An important thing to understand about spectral effects is that they can be created by using short time delays. Previously, when we implemented echo effects, we used a relatively long time delay, such that the signal's repetition is audible to a listener. If we shorten that time delay, the repetition is no longer going to be perceived as a distinct echo, but rather one fused sound. More importantly here, we're also going to see that some interesting things happen spectrally to a processed input signal. In this video, we're going to look at some of the foundational concepts for creating spectral effects by using short time delays. Then we'll be able to move on and implement these effects in MATLAB computer code. Let's start with a visual example to frame how we're going to think about this time delay. Here's the waveform of a signal, amplitude versus time. If we delay this signal, it's going to look as though that we've shifted the signal over to the right by some amount. This amount is our delay time. We can think about delay time in several different units. We've talked about this before, as sometimes it's intuitive for us to think about it in terms of units of seconds. We can also convert units of seconds to other units, like milliseconds, or if we're working with a digital signal and we know the sampling rate, we can think about it in terms of the samples of delay. These are 3 different units that all describe an equivalent delay. Now, when we're working with a shorter time delay, it's also helpful for us to think about other units. In this case, this is a relative unit compared to the length of the period or the length of a cycle. So for this signal, if we compare the blue signal to the red signal, this is actually 3/4 of a cycle that we've shifted the signal over. So it's relative to the length of a cycle. Or in terms of other units, this would be a 270-degree shift. Or we'll look at later on how we could also look at it in terms of radians. 3 more different units that we can use to describe this time delay. Now, the interesting thing comes up if we look at an example here with different frequencies. Let's just pick an arbitrary amount of delay. Let's say, for instance, this delay that we've introduced for this signal is 5 samples, that we've shifted it over to the right. 5 samples of delay. Now, if we were to apply this same exact delay that is equivalent to 3/4 of a cycle for this frequency, let's apply this same delay to a different frequency. So 5 samples of delay, but we have a lower frequency which has a longer period. So in this case, 5 samples of delay is actually equivalent to 1/4 of a cycle, or a rough approximation of that. So the same exact 5 samples of delay actually has a different amount of relative shift, 3/4 of a cycle versus 1/4 of a cycle. This becomes very important. We start to think about trying to create spectral effects. So just to summarize what we've seen so far, a time delay can be thought of in different units, including samples, or we could also include it and describe it in terms of its phase shift relative to the length of a cycle. This phase shift is going to be different for different frequencies. Call it a frequency-dependent phase shift. We can calculate this actually based on the number of samples of delay. If we know the frequency, then what we need to do is convert it over to some shift in terms of degrees or radians per 1 sample of delay. So let's look at an example here with 1 sample. So if we know some frequency, that's going to be cycles per second, what we want to figure out is what is the phase shift in terms of radians per 1 sample of delay. Or you could also convert it to degrees of 1 sample of delay. So how is this set up? What we need to do is cancel out our units of cycles and our units of seconds. So what we do is we set it up and we know that there are 2 pi radians for every 1 cycle, or it could be 360 degrees per cycle. So now our cycles are going to cancel. And then if we use our sampling rate, which is 1 for every 1 second, there are 48,000 samples. Now we're going to have our units of seconds cancel, and we end up with radians per sample. So we plug in whatever frequency we want, and we can figure out what's that phase difference or the phase shift that we introduce for that frequency. Let's look at a couple different examples where we actually plug in some values to figure this out. Let's say we're working with a sampling rate of 48,000. So let's start by looking at a high frequency. Actually, this is our Nyquist frequency, the highest frequency that we can record. So we're going to plug this in and look at the phase shift. So 2 pi times 24,000 divided by 48,000. What do we end up with in this case? So for this frequency, when we introduce one sample of delay, it's actually equivalent to a 180 degree phase shift, or pi radians. Let's look at another frequency on the whole other end of the spectrum, a low frequency, 1 hertz. Now, just because this is a frequency we can't hear doesn't mean it's not helpful. I think this just simplifies the math for us. Think about what happens for low frequencies. So let's plug this in, 2 pi times 1 divided by 48,000. You end up with some very, very, very small number. It is essentially a negligible phase shift, around 0 degrees phase shift. So if we compare the low frequencies to high frequencies, 180 degrees compared to 0 degrees. Now, what does this all mean? Let's look at actually how we create spectral effects then. So we understand what's going to happen when we have one sample of delay. Well, in terms of creating spectral effects, what we're going to do is set up parallel processing. We have a dry path here where we don't introduce any delay. And then we're going to have a wet path where we introduce one sample of delay. So this is just one type of spectral effect. And what do we do with these two paths? We actually add them together. So we're going to be combining the signals over here. Let's look at some different frequencies now. Consider what happens. So we've got our low frequency that we're going to put in, 1 hertz, that we feed through the system. So we can think of this, our blue signal here is our dry path. And then if we have our wet path with one sample of delay, we talked about before and saw that this introduces a negligible phase shift, about 0 degrees. So how do these signals line up? The blue signal and red signal are essentially right on top of each other. So what happens? We add these two signals together. We know what happens as audio engineers. You add blue plus red in this case. We describe that in terms of constructive interference. So adding these two things together, we get constructive interference. What's the general effect then? Our amplitude actually increases for this frequency when we feed it through this system because we're adding it together. Let's look at our high frequency then. So now, instead of 1 hertz, let's feed in our Nyquist frequency, 24,000 hertz. So I have our blue signal here, and we know that when we shift this signal by one sample of delay, that introduces 180 degree phase shift. So if we were to plot now the red signal that's been delayed on top of our blue signal, it's going to be completely out of phase with each other. So we're going to add together two signals here that are out of phase with each other. How do we describe that? We describe that as destructive interference. When you add them together, the amplitude actually decreases. So we've got some frequencies where the amplitude increases and some where it decreases. So how do we conclude what just happened? So spectral effects are created using short time delays. That's going to be an important thing that we make use of. We set up parallel processing so that we can combine delayed signals together. And now what we're going to have is a dry signal that we add with a delayed signal. What happens? Some frequencies have constructive interference and some frequencies have destructive interference. Therefore, the amplitude of some frequencies passes through the effect while the amplitude of other frequencies is cut, right? This is called filtering. Sometimes we have low-pass filters or high-pass filters, band-pass filters, notch filters, and we're going to look at how we can use this concept in order to set up just about any kind of filter that we like to create. We're going to analyze it, and we're going to design it, and we're going to look at implementing it in MATLAB in the next few videos.